Another mechanism by which elimination occurs is known as the E2 mechanism. And an example of that in a generic sense is shown here at the top of this slide. In this type of elimination, the nucleophile acts not as a nucleophile, but rather as a Bronsted base by virtue of a non-bonded pair of electrons, extracting a hydrogen from the substrate and causing the formation of a pi bond and loss of the leaving group all in one step. This type of process often competes with SN2, where if the nucleophile is a strong base, then the E2 pathway is preferred, whereas if the nucleophile is a strong nucleophile and a relatively weak base, then often the SN2 reaction is the preferred pathway. But in many, many cases, you end up producing a mixture of products. And we'll talk a little bit more about that as we move forward. It's worth noting here that these are sometimes called beta eliminations. And that designation comes from using the Greek alphabet to denote positions within the molecule. In this case, the carbon that bears the leaving group is our reference point and is designated as an alpha position. And then we move throughout the molecule using the Greek alphabet as designators. And so the next carbon would be a beta carbon. And the hydrogen that is attached to that carbon is known as a beta hydrogen. So E2 eliminations are sometimes referred to as beta eliminations because we are removing two groups, a hydrogen and a leaving group, that lie beta to one another in the structure. So let's draw out the mechanism for this particular reaction, where sodium ethoxide, you can see here, is our base. Sodium ethoxide is that type of structure that can be both a Bronsted base and a nucleophile. Here we're just going to focus on the elimination reaction that occurs when this 2-chlorobutane is treated with sodium ethoxide. And you'll notice here that we produce two products, and we're going to talk about these product mixtures in a little more detail here as we move forward. So looking at the first product, if we draw out our substrate as a bond line formula, we want to focus on a hydrogen that lies at this position, beta to the chlorine. And we can abbreviate the ethoxide ion this way using ET for the ethyl group, just for simplicity. And these are one-step mechanisms, so we're going to use an arrow from our base to the hydrogen to indicate that the deprotonation is occurring. The electrons in the carbon-hydrogen bond are what become the pi bond between the alpha and beta carbon in our substrate, and the chloride leaves as a chloride ion. And so that mechanistic pathway leads to the 2-butene product, and it would actually be a mixture of cis and trans, but primarily the trans. And again, we're going to look at that in more detail here in a little bit. The second product is also a beta elimination. So it's the same substrate reacting again with ethoxide acting as a Bronsted base. But in this case, the beta hydrogen lies at this position in the structure, but mechanistically the same 3 arrows. So the base removes the proton, the electrons left behind become the pi bond, and chloride is our leaving group. And so this would give us the 1-butene product that we produce. So let's look at some of the details of these reactions more closely. So first, let's look at the interplay between E2 and SN2. We know from our previous look at substitution reactions that tertiary substrates, such as this T-butyl bromide, do not undergo SN2 reaction. There's too much steric hindrance for the nucleophile to access the sigma star orbital of the carbon-bromine bond, and substitution doesn't occur. The E2 mechanism, however, doesn't suffer from the same steric constraints. And what is needed is the ability of the nucleophile acting as a Bronsted base to access one of the hydrogens. And in T-butyl bromide, they are freely available and on the periphery of the molecule. And so we find that these tertiary substrates fail to undergo SN2 even in the presence of good nucleophiles, but will easily undergo E2 elimination. And you can see if you follow the arrows here, we would end up with this alkene product. If we now look at less hindered substrates and the interplay between E2 and SN2, we get more information about kind of how this reaction plays out in that regard. Here at the top of the slide, we have a secondary substrate, and when treated with this chloride salt, the tetrabutyl ammonium iodide here is just acting as a simple counterion. Chloride is the reactant. You can see by looking at these products that chlorine can act as a nucleophile, and we get a substantial amount of SN2 product. But the chloride ion can also act as a Bronsted base and deprotonate this compound, and we get a significant amount of E2 product. If we look and think about where the chlorine is going, the SN2 reaction is the direct displacement of bromine by the chloride. And that's a reasonable proposition given that this is a secondary carbon that the nucleophile is interacting with, and chlorine is a quite small nucleophile. But the other reaction that can occur is that the chlorine acts as a Bronsted base, removes the proton, the electrons in that carbon-hydrogen bond become the pi bond, and bromide is the leaving group, and we end up with the E2 product. And this is typical of secondary substrates, that they will often give these mixtures of both substitution and elimination. If you look at the bottom of the slide with a primary substrate, you can see that the preference is for substitution by an SN2 mechanism. So same reagent we saw above, with chloride ion as our reactant, and in this case, the chloride ion is doing the typical SN2 reaction, and we're getting virtually no elimination. So the nature of the compound that bears the leaving group has a big effect on whether the preference is for elimination versus substitution. An additional aspect that's important is the stereochemistry of the E2 reaction, and specifically the stereochemistry of the substrate as it undergoes this elimination. Because remember, this is a one-step elimination where the base deprotonates, pi bond is formed, and the leaving group leaves all at the same time. And here we find the different conformations between the two leaving groups. And what's important is that there needs to be alignment, that the bond between the carbon and hydrogen needs to be aligned with the bond between the carbon and the leaving group. And there are two ways that can happen. That can happen if they are anti to one another, or it could happen if they are eclipsed. Now, eclipse conformations tend to be very highly strained unless there's something that locks it into that conformation, so it's relatively rare to find eliminations occur in those situations. But anti-eliminations, particularly in acyclic compounds, are easily formed and are typically quite stable. So what we find here is that the reaction won't occur if you do not have full alignment. So in this case, we have a dihedral angle of 120 degrees, and that structure is inert to the E2 elimination. Here we have the carbon-hydrogen bond and the carbon-leaving group bond gauche, and this is also inert to elimination. It's only when we have alignment that these occur. And the most important is this anti-arrangement. That's by far what we find happen most commonly. Less important is the eclipse conformation, but we do find examples of that in the literature because of the way the molecule is constrained in its conformations. So looking a little more closely at this, if we look at the Newman projection of the transition state for an E2 elimination, and that's what's shown here. The base is not indicated, but in the transition state, we have partial bond between carbon and hydrogen as this bond is breaking. We have a partial pi bond forming, and we have a partial bond between the carbon and the leaving group. And the most efficient orbital overlap, the maximum orbital overlap, occurs when these are aligned in the fashion you see here, such that the hydrogen and the leaving group are anti to one another. There's a name for this, and this arrangement in the structure is we say that the hydrogen and the leaving group are anti-periplanar, and you'll hear that term from time to time moving forward in the course. It's the orbitals that are involved in the transition state that give rise to the necessity for this anti-periplanar arrangement, and this is illustrated a few ways here. So this particular simple reaction shown here at the top of the slide is hydroxide reacting with this ethyl chloride. And if we draw in the curly arrows for the mechanism, it's as we've seen previously. And walking you through what's illustrated here is it's a single step mechanism. All the bond making and bond breaking happen at the same time. So if you think about it, there are 1, 2, 3, 4 bonds involved in that transition state. We're forming a bond between oxygen and hydrogen, breaking the carbon-hydrogen bond, forming a pi bond, and breaking the bond to the leaving group, all at the same time. So a concerted process. Here it is shown with models. The hydroxide ion lone pair taking the proton, forming the pi bond, and the halide ion leaving. If you model the transition state, and that is shown here, you can see all of the orbitals that are involved in that transition state structure. And here is that forming bond between oxygen and hydrogen. Here is the breaking carbon-hydrogen bond. You can see that that orbital extends across both carbons, so we're starting to form a pi bond here on both sides of what's going to become a planar alkene, and we're starting to elongate and break the bond to the halide, and we ultimately form our products that we see there. So earlier we'd drawn a mechanism for a simple elimination reaction of 2-chlorobutane, and we noted that it gave 2 products. Well, it turns out this is a very old observation dating back to the end of the 19th century by a Russian chemist by the name of Zaitsev. And by the way, you'll see this name spelled various ways. Here it's spelled with an S. You sometimes see it spelled with a Z. It's a phonetic spelling of a Russian name. And curiously, Zaitsev was a colleague of Markovnikov's to some extent. The story has it that actually the two of them didn't get along very well, but you can look that up. You can Google it. So let's look a little more closely at how elimination reactions occur to give multiple products and what might be the major product. The Zaitsev rule, as Zaitsev stated it at the end of the 19th century, was that there was a preference for deprotonation of the substrates at the carbon that bore fewer hydrogen substituents. And if we draw out where the hydrogens are that can react in this substrate, let's look at this 2-bromo hexane. So remember, our alpha position is where the leaving group is located, but the hydrogens would be beta to that. And so the hydrogens that can react under these conditions would lie on this methylene group and on this methyl group. Zaitsev's observation was there was a preference for removal of the hydrogens from the carbon that bore fewer hydrogen substituents. So the methylene group has 2 hydrogens, whereas the methyl group has 3. Zaitsev's observation, which he had no explanation for, was that there was a preference for formation of the major product from the carbon, removal of the hydrogens from the carbon where there are fewer, so here. And so this would be the transition state for that reaction. If we draw the curved arrows in for what's going on, we have methoxide here acting as a Bronsted base, removing one of these hydrogens, bromide leaves, and you can see that we in fact produce this 2-hexene product. So that's one of the 2 products. The other product is shown here. So same reaction, same substrate, same base, so a methoxide reacting with this 2-bromohexane. Slightly different transition state. We're removing one of the hydrogens from the methyl group here at the end. That means the double bond would form at this position, and we move one with the 1-hexene product. So the product that is the major product in this case is the so-called Zaitsev Rule product. There's actually a name for this minor product. It's sometimes called a Hofmann product. And we're going to look at a couple examples where the Hofmann product can actually be favored. And one of those is if the base is sterically bulky. Now, methoxide is quite small. We think of it as sterically small. But there are bases that are kind of large and bulky. And in those cases, they actually prefer to remove the hydrogen at the end of the molecule because they're more easily accessible than the hydrogens in the middle of the molecule. So that difference between a small base and a bulky base is illustrated here. So here these red clouds kind of indicate large electron clouds because of the structure. So small bases generally have kind of equal ability to pull hydrogens off regardless of where they lie within the structure, whereas these large bulky bases, the rest of the molecule starts to get in the way and we get steric interference, and so we get less deprotonation at these more substituted carbons with the bulky bases than we do with the smaller bases. Now, this isn't typically going to completely shift the distribution, but it will change it. So here we have this 2-iodobutane, one reacting with methoxide, the other reacting with this T-butyl oxide. And you'll notice that this T-butyl group, this thing is actually quite large, whereas the methyl group is rather small. And changing the base, you'll notice changes the proportions of the product. So here we have the proportions of these 2 elimination products. We get about a 5-to-1 mixture of the Zaitsev product versus the Hofmann. But with the large base, you can see that the proportion of the Zaitsev product drops. And so we're getting less than a 4-to-1 ratio between the 2. It doesn't completely favor the Hofmann, but it changes it considerably. And so you can see as a chemist, if you're trying to produce one of these 2 products, let's say you're interested in the Zaitsev product, you want to make sure that you're not using a bulky base and you're actually using a smaller base in favor of that reaction. Now, finally, there's one particular situation that doesn't involve the base, but rather involves the leaving group that can lead to large proportion of Hofmann elimination product. And that's shown here where we have as our leaving group, we have an ammonium ion. So this is an ammonium salt. It's a trimethyl ammonium salt of this 2-aminobutane. And this ammonium salt is sterically very large. Think of this as almost the size of a T-butyl group. And I'm going to highlight that so that we understand that its steric size is extremely important. And now if we think about the elimination reactions occurring in the 2 different positions, so remember this is a beta elimination, so we can remove hydrogens from either this carbon here or this carbon over here to give the 2 products that are shown. Removal of the hydrogen at this methylene group produces the Zaitsev product. Removal of the hydrogen from the methyl group produces the Hofmann product. If we look very closely at the conformations that the molecules have to adopt in order for this reaction to occur, we can see that in this situation, the conformation that leads to the Hofmann product is considerably less strained than the conformation that leads to the Zaitsev product. So that's what's shown here below. First, let's look at the conformation that the molecule has to adopt in order for elimination to occur to give the Zaitsev product. And what we have is our leaving group in the form of this trimethyl ammonia molecule. We have the methylene group here at carbon number 3 and one of the two hydrogens. And we have an orientation where the hydrogen is anti to the leaving group. Here it is shown as a Newman projection. And so the reactive hydrogen, let me highlight the reactive hydrogen here. I'll do that in green. The reactive hydrogen lies anti to the leaving group. And in that conformation, you notice that we have this gauche interaction between the methyl and the trimethylammonium ion. And this is particularly bad given the size of that trimethylammonium ion. So this is going to be a relatively unstable conformation for the molecule to adopt. It's actually worse if this rotates and the methyl group goes over here, because then you have an additional Gaussian interaction. So either way, this is a very strained conformation for the molecule to adopt before it reacts. On the other hand, down below, if we look at elimination of one of the hydrogens from the methyl group on carbon number 1, that elimination, looking at down the carbon 1,2 bond, here is a Newman projection, you can see in that elimination, we don't have that bad steric interaction. There are hydrogens adjacent to the trimethylammonium ion. And so this conformation is much, much lower in energy and significantly more stable. And as a result, the molecule can adopt it, and it's much more reactive in this conformation. And we get predominantly the Hofmann product.